All right, so this video is going to focus on 6.5. If I look here, it says graph the data first of all. So you have your x and you have your y, and you start graphing it out. And we have this linear graph. For the second one, we look to see if it's linear as well. And when I do it, I'm going to notice that it is also linear. For this one here, graph it out. Again, totally linear. And the thing that I'm really focusing on with all three of these is the starting point, where it's going to start or cross that x-axis or y-axis. So in this case, it's going to probably come down at 0, 0. This right here is absolutely proportional or direct variation. This one here is not direct variation because it does not go through the point of origin. And this one here, if I go down to go by 2 every time, right? So that would be 0 or 0, 1. So this is also not direct variation. Then I want you to kind of complete this table here. So if I have 1/2 to the x power, and if I start doing this, 1/2 to the 0 is 1. And then to the first is 1/2, of course. And then we keep on doing this, and what happens is I end up getting this function that is parabolic in nature. It looks kind of like this here. So here are my various answers. For this here, I have 1/3 to the x power. We're going to do the same kind of thing where we have to plug in a 0. I have 1. And then I have 1/3, and then 1/9, and so on. And how can we use a graph to represent the relationship between quantities without using numbers? That's what we're going to really focus on today. So if I look at this here, what I want you to do is kind of think about what is happening between water level, which is your dependent variable, and your time, which is your independent variable. So it appears that you have a constant amount of water, maybe in a bathtub, or it's, there's a little bit. It's not at 0, so perhaps you've already you filled the bathtub a little bit, and then it gets cold. So you start putting more water in until the water is warm enough. You then let it sit for a while, and then you're done with your bath, so you let it drain. And this is an example of what this graph is telling us. Even though we don't have numbers to understand it, we're just looking at the relationship between the direct or this dependent variable and this independent variable. So now we're going to look at these and think of various ways that you could have stories of this here again with speed and time. What kind of stories can you have? And it says that you're riding a bike. So I'll give an example of one of them. So perhaps we'll just look at this first one here. And if I look at it, it's going speed. So maybe I'm going down a hill, not up a hill, down a hill, because I'm going faster. And then I'm going down a really steep part of the hill. And then all of a sudden I'm going up a hill. And it's almost backwards from what the graph looks like. But if you think about speed, your speed, of course, is going to decrease as you're going up a hill. So that's the kind of relationship I want you to think about as you watch this and you try doing these. Here's some other ones. And then it says, how are these graphs similar and how are they different? Well, in both cases, they start at the point of origin at 0, 0. This one here, of course, is not going to be linear. It is going to be exponential or something. Something else is going on here. And it's going up a little bit quicker. This is a constant rate. They're both increasing. But if I look here, this is getting steeper over time. So at first, this one is steeper, of course. But as you start going through more time, it's going up faster. And same thing here with looking at how they're similar. If I look at it, although I don't have numbers, I can tell that this is both starting at the same place, essentially, and it's getting slower as time goes on. This is a constant rate, and this is more of an exponential or something's going on here where it's getting lower. All right, try to figure this out, of course. And then this is some other examples of what is going on here in terms of speed and time in a car. So, of course, maybe you're racing ahead to a stoplight. You stop at the stoplight. You race ahead again, so you're going fast. Well, actually, this can't be a stoplight because of the fact that I actually am going some miles per hour. So if I look here, I'm racing ahead, and maybe I hit my cruise control. And then I want to pass a car, and I hit my cruise control. And then I start decelerating to a stop. This shows temperature throughout the day in 2 cities. So I have Belfast, Maine, and Newport, Oregon, if I look at it. So as the day starts off, it appears that as the day goes on, it gets warmer and then it gets cooler, which is kind of normal. The sun comes out, it gets warmer, then it starts getting cooler at night. If I look at Newport, Oregon, it's a little bit different. So at least in this case, perhaps it was during the day and it's going towards night. Here's my night temperature, and then the sun's starting to come back up again. If I look here, it says that, so there's a pelican and an osprey, and they're showing the vertical distance in which a pelican or osprey go to look for their prey. And so a pelican seems to like kind of float around above the water for a while, looking for the fish, kind of goes in, looking really close to the water, then maybe we'll drag down and get the fish. Or an osprey is a little bit higher up in the air, kind of comes down a little bit lower, but then goes straight down into the water to get its prey. So here's an example where a fully charged battery loses its charge at a constant rate until it has no charge left. Then you plug it in and recharge it fully, and then it loses its charge at a constant rate until it has no charge left. And what I'd like you to do is try to think about what would this graph look like. Again, there's no numbers here. It's just basically thinking about the relationship between the amount of battery life and the time in which you use it. And that is 6.5.